Welcome to my talk on faster coherent quantum algorithms for phase, energy, and amplitude estimation at TQC 2021. Thank you very much to the organizers for letting me present my work here. This talk is based on a manuscript that I uploaded to the archive in March 2021. Let's begin by defining the problem of coherent phase estimation and coherent energy estimation. So as input, we are given either a unitary with eigenvalues e to the 2 pi I lambda j, or a Hamiltonian with eigenvalues lambda j. I'll refer to the lambda j collectively as the eigenvalues. That way we can talk about both problems at once. The problem is this: we are given some unknown superposition over the eigenstates psi j, as well as an ancilla register that's initialized to the all zero state. And we compute an n-bit estimate of the corresponding eigenvalue lambda j into this n-bit register. We do so without damaging the superposition weighted by the alpha j. This kind of operation has many applications in the literature. One application is that of quantum metropolis sampling, which is essentially a random walk over the eigenspaces of the Hamiltonian that is guaranteed to converge onto a Gibbs state. I expect this algorithm to be useful in practice, so therefore having a fast algorithm for energy estimation, which is repeatedly used as a subroutine by this algorithm, is valuable. Another application is that of non-destructive amplitude estimation. That is, we're interested in estimating the amplitude of a quantum state on some projector, but we're given only one copy of that quantum state, and we can't destroy it because we want to use it for other things. This is required as a subroutine by a line of work that implements quantum algorithms for Bayesian inference and for partition function estimation. In the prior art, this would have been accomplished via phase estimation, so just the textbook method. So this is done as follows. We initialize a register over various times t, and then apply our input unitary t times. Then we apply an inverse quantum Fourier transform onto that t register and obtain a decent estimate of the phase lambda j. Now that estimate is only correct with probability 80% or so. So in order to achieve high probability of success, we must amplify. This is very easy to do classically. We just sample many such estimates and then take the median. However, on a quantum computer, this is somewhat cumbersome to do. We need to allocate another register for every single sample and then run a quantum sorting network on all of those ancilla registers, copy out the answer, and then uncompute. This is a very expensive circuit to run coherently, and I think we can do better. An improvement of phase estimation is already common in the literature. This is called iterative phase estimation. It assumes that we're giving an eigenstate of psi j and estimates each bit of the energy lambda j 1 bit at a time. This algorithm is a lot simpler and requires much fewer resources, but as I said, it requires the input to be an eigenstate of the unitary in question, which is not necessarily the case in our situation. Now, there is a recent line of work on amplitude estimation, modernizing amplitude estimation from the method that is based on textbook phase estimation. Both of the papers in this line of work, however, are highly destructive. They require many copies of the input state, each of which is destroyed after taking a sample. Now, the line of work that performs Bayesian inference and partition function estimation uses an algorithm based on phase estimation. However, then it succeeds at repairing the input quantum state after measuring it in a very clever basis. This repair process doesn't succeed with probability 1, but it can be repeated several times until we have a repaired copy of the input state. We would prefer, however, to just have a quantum circuit that we run once and produces a copy of the input state again, as well as an estimate, without requiring this classical adaptivity. So in order to describe our algorithm, we require block encodings. Block encodings are a tool for manipulating non-unitary matrices on a quantum computer. It's described comprehensively in this work by Gillian et al. We achieve manipulation of non-unitary matrices on a quantum computer by simply packing that matrix A into the top left corner of a unitary U sub A. U sub A is our block encoding of A. The only requirement is that the matrix A is bounded in spectral norm. Other than that, A can be anything. It does not have to be Hermitian. It does not even have to be square. So how would we implement an application of a block encoded matrix A? That is, we have some input state psi and we want to produce as output A times psi. Well, we allocate an ancilla register in the 0 state, apply our block encoding unitary on both the ancilla register and the input state, and then post-select that ancilla register to be in the 0 state again. The fact that that post-selection doesn't necessarily succeed with probability 1 reflects the fact that the state A times psi might be under-normalized. This is because the matrix A has eigenvalues less than 1, potentially. For an excellent review article on block encodings, I recommend this work by Martin et al. This work features both a review of block encodings, a review of various quantum algorithms, including Hamiltonian simulation and quantum matrix inversion using block encodings, and also features an independent discovery of this work's phase estimation algorithm. Let me briefly outline the tools that we have to manipulate block encodings in the next few slides before discussing the actual algorithm. So just like with unitaries, given two unitaries, we can multiply them together, we can take tensor products of them. But additionally, with block encodings, we have the ability to take linear combinations. This is accomplished as follows. So say we are trying to prepare a block encoding of the linear combination some I P I A I. We allocate an ancilla register that contains a Q sample of the distribution over which we would like to take a linear combination. We then apply, controlling on that ancilla register, the block encoding corresponding to that term in the linear combination. And then we post-select on that Q sampled state again. By taking linear combinations of Pauli matrices, for example, we can now achieve block encodings of basically any Hamiltonian of interest. So therefore, this is a very useful technique, particularly in physics. Now, another very important primitive for block encodings is that of singular value transformation. So for simplicity, I'm going to be presenting eigenvalue transformation here. We're given a block encoding of some Hermitian matrix A with eigenvalues lambda I and some polynomial P of X. Our goal is to apply that polynomial to every eigenvalue of A. The cost of this operation is the degree of the polynomial P, and this does not work for any polynomial. This only works for a restricted family of polynomials. However, we can expand, we can go beyond those restrictions by complementing singular value transformation with the linear combinations technique that I presented earlier. The circuit for this is very simple. It involves repeated application of the block encoding U and U dagger, as well as various phase rotations, e to the I theta ket 0 on the ancilla register. The angles encode the polynomial. The reason why I emphasize the circuit is to show how few ancilla registers it requires. Linear combinations of unitaries on the previous slide required adding another ancilla register, which is potentially very expensive. But here we didn't actually need to add any ancillas whatsoever. The ancilla efficiency of singular value transformation is one reason why I believe our new algorithm is so practical. Now we're ready to describe the actual procedure. To do so, this procedure uses a block measurement lemma which is a new tool developed for this work. So say you have a projector pi, and you're interested in computing whether or not you're in the eigenspace of that projector into an ancilla register. So this is accomplished by the following isometry. Say you have an approximate block encoding of this projector pi, then there exists a quantum channel that implements something close to this isometry. The quantum circuit for this is very simple. It simply involves the block encoding unitary of the projector pi. Then you compute into an ancilla register whether or not we are in the zero eigenspace. Then you uncompute and you discard the intermediary ancilla. The analysis of the circuit is very simple, provided you have an exact block encoding of a projector, but it actually gets somewhat cumbersome when your block encoding is approximate. So to deal with this, I developed an analysis trick where we simply consider post-selecting on zero rather than discarding the output register. The total error of the quantum channel can then be written as a linear, can be bounded by a sum of the error when the post-selection succeeds, plus the failure probability of that post-selection. Now we're ready to describe the actual algorithm. So remember, our goal was to compute an n-bit approximation of lambda j. I'm going to say for now that this is simply the floor of lambda j times 2 to the n. For every bit, starting with the least significant bit at k equals 0, and then the most significant bit at k equals n minus 1, we prepare a projector whose eigenvalues indicate the kth bit of lambda j. The kth bit of lambda j is either 0 or 1, so therefore this is a projector. The way we construct such projectors is via singular value transformation. That is, for each k, we construct a polynomial piece of k such that when we apply it to our Hamiltonian, we obtain an approximate block encoding of this projector pi sub k. Now, essentially, all we need to do is find a polynomial piece of k that approximates the kth bit of its input. Finally, now that we have our block encodings of our projectors, we can use the block measurement lemma from the previous slide to compute the estimate lambda j 1 bit at a time. So what does the kth bit of lambda as a function of lambda look like? Well, it looks like this, these kind of square wave functions. So for the least significant bit, you can see that the bit alternates between 0, 1, 0, 1 at a very high frequency, but the most significant bit oscillates between 0 and 1 very slowly. The way that I built this figure is that you can simply read off the binary expansion from the x-axis. Consider, for example, 0.0110. You can read off that this falls from the most significant bit into the least significant bit, 0110. Now, immediately we run into a problem, which is that no polynomial looks like this. Polynomials are continuous functions, whereas this function is very discontinuous. It has very many discontinuities. It is impossible to approximate a discontinuous function using a polynomial. You might have a polynomial that is very close to 0 and 1 in the middle of each of these regions. But in the regions where we transition, where we jump from 0 to 1, the quality of our approximation is necessarily going to be poor. To address this issue, we add an assumption on our input, which is simply that no eigenvalues are allowed close to these discontinuities. So we call such a restriction a rounding promise. It is a restriction on our input unitary u or our input Hamiltonian h. So for some alpha, we demand that for all multiples of 1 over 2 to the n, there are no eigenvalues within a range of width 1 over 2 to the n. This is chosen such for the following reason. So the width of each disallowed region is 1 over 2 to the n, and there are 2 to the n many such regions. So the total fraction of the range 0, 1 that we are disallowing via this promise is alpha. A more generous rounding promise would involve a smaller alpha. Now, this is not just a restriction of our work. This is actually a restriction for any coherent phase estimation algorithm. We briefly argue this here. So consider a quantum circuit that uses applications of control U on some quantum state psi j. And that quantum circuit, since it is a coherent quantum circuit, doesn't have any measurement in it. Via an argument very similar to the polynomial method for constructing lower bounds in quantum query complexity, we can see that the amplitudes of that quantum states, of those quantum states, must be some polynomial in the phases e to the 2 pi I lambda j. So we have some superposition over estimates lambda hat and potentially some garbage depending on lambda hat. The amplitude of each particular estimate lambda hat is going to be a polynomial, which is a continuous function in lambda j. Now, because of the continuity of these amplitudes, we must have some spot to interpolate between the 0 and 1 values that we saw before. In order for our estimate to work well or to work with high probability, we require that our amplitudes are either close to 0 or close to 1 in magnitude. And furthermore, we require this if we want uncomputation to work. However, we see that because of the continuity, it is impossible to make this work for every possible lambda j. So therefore, there simply must be some regions where eigenvalues are disallowed. The only way to avoid this problem is to measure the quantum state. Measurement allows us to introduce discontinuity. So after having made this assumption, our stencils for our polynomials look something like this. We are still required to be very close to 1 in the 1 regions and very close to 0 in the 0 regions, but we are given a little bit of room, which is the gray regions, around each multiple of 1 over 2 to the n, enough room to interpolate between 0 and 1 using our polynomial. The degree of the polynomial is inversely proportional to the width of this gap. So the more narrow this gap, the higher the degree of the polynomial. Therefore, since we are trying to have high performance, which means lower degree, we would like these gaps to be as wide as possible. We can use a trick inspired by iterative phase estimation to make the degrees of the polynomials for the more significant bits somewhat smaller by computing the least significant bit first and then shifting the phase that we estimate for future bits accordingly. So say we measure the least significant bit and get a 1, we simply subtract off 1 over 2 to the n from the phase. This would guarantee that for the more significant bits, the phases don't take certain values, which manifests as me expanding these gray regions. So now, while the least significant bit, the polynomial is still very expensive, for the more significant bits, the polynomial has more time to interpolate between 0 and 1, and therefore we can get away with a lower degree. This optimization essentially manifests by taking a factor of n out of the runtime. So rather than the runtime being 2 to the n times n, it is just 2 to the n. So now that we have established what polynomials we would like, let me show you how to actually make polynomials that fit this description. So we begin by manufacturing a cosine, specifically cosine squared, so that we are between 0 and 1, at a frequency that lines up with the bit that we're trying to estimate. For unitaries, this is very simple. We simply use linear combinations of unitaries with the identity, to obtain a block encoding with eigenvalues e to the 2 to the n minus k pi I lambda, quantity plus 1 over 2. This is proportional up to a complex phase to cosine. For Hamiltonians, we must make this cosine ourselves. To do so, we use the Jacobi-Unger expansion, which is a tool for manufacturing very high quality polynomial approximations to cosine and sine. This is, for example, used to achieve Hamiltonian simulation as well. So using these tricks, we can begin with a block encoding whose eigenvalues are cosines of various frequencies of the eigenvalue lambda. By choosing the frequencies correctly and scaling and shifting the output, we achieve polynomials whose troughs are in the 0 regions and whose peaks are in the 1 regions. So now we're already in very good shape, especially for the most significant bit. For the most significant bit, the cosine in the 1 region is already very close to 1. And in the 0 region, it is very close to 0. However, for the least significant bit, this is less true. We're only close to 0, very close to the middle of the 0 bin, and close to 1 in the middle of the 1 bin. In order to make this actually work for us, we need to take values of where the cosine is less than 1/2 and smush it down to 0, and take values of the cosine that are greater than 1/2 and push it up to 1. If we view the output of the cosine, which is between 0 and 1, as a probability, then we actually have a name for this sort of behavior from theoretical computer science. It is called amplification, taking a probability that is more than 1/2 and making it 1 with high probability, taking a probability that is less than 1/2 and making it 0 with high probability. So this is our goal with our amplifying function a of p. If p is less than 1/2 minus eta for some gap eta, then we want a of p to be less than delta. If p is greater than 1/2 plus eta, then we want a of p to be greater than 1 minus delta. Such an amplifying polynomial could be constructed, for example, just using classical amplification. Classically, we could take a coin that is heads with probability p, toss that coin many times, and then take the majority vote of the answers. We know just from Chernoff-Höfting bounds that the majority vote of many coin tosses is very likely to be close to 0 or 1. Furthermore, if you expand the probability of more than half of m coin tosses coming up heads via the binomial expansion, you will find that this is actually a polynomial. So we can apply this amplifying polynomial to our cosine using singular value transformation. This achieves a degree of 1 over eta squared, which is actually less than optimal. So instead, I will be using a quantum amplifying polynomial developed by Lo and Chuang in 2017. So this is constructed via a series of polynomial approximations. We begin by writing amplification via the sine function, which is just achieved by shifting and scaling. Sine can be approximated with the error function, which is in turn approximated by an integral of a Gaussian function, and the Gaussian function can then be approximated by a polynomial via the Jacobi-Unger expansion, by a different variant of the Jacobi-Unger expansion. So this quantum amplifying polynomial has very good constant factor performance in terms of degree, which is why I use it for this work. So if we apply this amplifying polynomial to our cosine, we get something that looks like this. As before, we have a function that is very close to 1 in the 1 regions and very close to 0 in the 0 regions. For the most significant bit, the amplifying polynomial needed to do very little work. we could have chosen a very large eta. So the degree of the amplifying polynomial is very low. On the other hand, for the least significant bit, our eta is very small. So therefore, that polynomial needed to be much higher degree. And this completes the description of the algorithm. We take these polynomials, apply them to our Hamiltonian. This gives us a projector whose eigenvalues indicate the kth most significant bit. And then we use the block measurement lemma in order to extract that eigenvalue into an ancilla register, which is just our output. Let us discuss the performance of this algorithm. The performance depends on three parameters: the desired precision of n bits, the probability with which we succeed, or rather the diamond norm, the error in diamond norm of the resulting quantum channel, and our gap parameter alpha, which is essentially the fraction of lambdas that we do not allow. Now, phase estimation, the textbook method, was already asymptotically optimal. This new method, as well as the textbook method, both achieve a runtime of 2 to the n 1 over alpha log 1 over delta. So our improvement is strictly in terms of constant factors, as well as ancilla requirements. So recall that textbook phase estimation demanded taking many estimates, each into its own ancilla, and then running a quantum sorting network. So that means the ancilla cost of textbook phase estimation actually depends on the desired accuracy as well as the gap parameter alpha. Our new method only achieves amplification through singular value transformation alone, and therefore does not require any new ancillae. So the ancilla count is linear in n. In fact, for a particular version of the phase estimation algorithm, we don't require any ancillae at all, other than, of course, the output register. In terms of constant factor improvements of the query complexity, of course, this is going to depend on the particular situation. Say you're doing energy estimation, you may be using the Trotter approximation to be performing Hamiltonian simulation, which you then feed into your phase estimation algorithm. For comparison here, I compared Hamiltonian simulation using block encoding based methods together with phase estimation to our method, which relies entirely on block encodings. And then I chose values of our parameters large or small enough such that the speedup stabilizes. And for those values, I find that the speedup converges to roughly 14x for phase estimation and 20x for energy estimation. Let me conclude by outlining how to use energy estimation to perform amplitude estimation in a non-destructive manner. So recall, we are given a quantum state psi and a projector pi, and our goal is to estimate the norm of that projector acting on the quantum state. We are given exactly one copy of the quantum state, and we are not allowed to destroy it. And we are given the reflections about the projector as well as about the input state. So this is useful in a situation where reflecting about the input state is cheaper than preparing the input state. This happens in those algorithms for partition function estimation, for example. Our algorithm proceeds as follows. We use linear combinations of unitaries to convert our reflection oracles into simply block encodings of the projector pi and the quantum state psi. And then we multiply these together to obtain a block encoding of a Hermitian matrix with eigenvalue a squared and eigenvector psi. Now we simply plug A as a Hamiltonian into our energy estimation algorithm, which then extracts an estimate of A squared onto an ancilla register. Now observe that since the input state psi is an eigenstate of the Hamiltonian, the output register ket A squared is unentangled with the input state psi. This means that we can measure the output register without damaging the input state psi. So therefore, we no longer have the restriction of the rounding promise, which used the fact that quantum algorithms that cannot measure can only implement continuous functions in their amplitudes. Because we can measure, we can achieve discontinuities, and therefore the rounding promise is actually not required for this application of energy estimation to amplitude estimation. Thank you very much for your attention. I want to thank my advisor, Scott Aronson, as well as several other scientists with whom I had very productive conversations with while I was preparing this work. If you have any questions about this, please don't hesitate to contact me at my email address.